This is a lesson introducing rotational motion. Up until this point in the class, we've only been talking about motion that was describing things moving from one place to another place, moving from here to there, so to speak. And that is a kind of motion that we call translational motion. But there's a different type of motion, and that is for rotating objects that are turning. So you can turn a wheel and have it rotate even though it's not really going anywhere, so to speak. So we call that kind of motion rotational motion, or sometimes we call it angular motion. And this is a good point in the semester to study rotational motion, because the easiest way to understand rotational motion is by analogy with translational motion, so it is a good way to kind of go back over some of the things that we did at the very beginning of the course on translational motion, and that'll help get you ready for the final exam, since it's coming up before very long now. So if you remember back at the beginning of the semester, what we did when we first started motion was we needed to develop a vocabulary. We defined some terms so that we could talk about motion in a precise way. We defined things like displacement, which we gave the symbol, say, delta x, or maybe x minus x0. We said that if displacement is changing with time, then we called it velocity. And if the velocity was changing, in other words, if we're not going at a constant speed, then we called that acceleration. Okay, well, in rotational motion, we're going to do something similar. Right. First, we need to define what do we mean by motion in a rotational sense. So if you think of something like, say, a bicycle wheel, and we mark this line as being the starting point of the wheel, and we'll put another line right there on the wheel itself. I'll put a dot right there. Okay, so that we can sort of notice when the wheel turns, we'll see that dot move. Okay, and we'll call right here the original location of that dot, we'll call theta 0. But then sometimes, so we might rotate the wheel so that maybe the dot is down here now. Here's our original reference line. And the new position of that dot we will call theta, the new angular position of that dot, so that the angle between the original angle and our final angle will be what we call our angular displacement, or delta theta, which is theta minus theta 0. Okay, so just like we had delta x before, which was x minus x0, we have delta theta now, which will be theta minus theta 0. Also, just like in translational motion, quite often we just let x0 be equal to 0, and we don't have to worry about it. In rotational motion, quite often, theta 0 can be treated to be 0, and you often don't have to worry about it. Okay, well, what if the angular displacement is changing? Perhaps my wheel is continuing to rotate. In that case, its angular displacement will be changing. So I can define the change in angular displacement over time as angular velocity, which has the symbol lowercase omega. It looks like a W. Okay, but it's pronounced omega, and it is called the angular velocity. Perhaps the angular velocity is not constant. Maybe the wheel is speeding up or slowing down, in which case I have a change in angular velocity, which we will call angular acceleration, and it has the symbol lowercase alpha, which looks like a fish with the right side of the tail not being closed. Okay. Then, if you remember what we did after we defined certain terms back at the beginning of the semester when we were learning about translational motion, we learned that there are relationships among these quantities, displacement, velocity, and acceleration. We called those relationships the kinematic equations. We had equations like x equals v0t plus 1/2 at squared, v equals v0 plus at, and v squared equals v0 squared plus ax. Well, we can do something very similar with relationships among the rotational variables. We call them the rotational kinematic equations. Theta equals omega 0 t plus 1/2 alpha t squared. Omega equals omega 0 plus alpha t, and omega squared equals omega 0 squared plus alpha theta. Now, the kinematic equations for rotational motion, they look a little bit more intimidating than the ones for translational motion because they've got the Greek symbols in them. But if you can remember, when it's time to work problems, that you approach rotational kinematics problems in exactly the same way you approach translational kinematic problems, then you won't have any difficulty. So let's work an example using the rotational kinematic equations, and I will show you that the same approach to translational kinematic equations works with the rotational kinematic equations. Okay, so I'm going to go ahead and erase the translational ones so we have some room to work. Okay, so let's say that we have a potter's wheel, which initially is not rotating, so we'll say it's at rest, and it spins up to 100 turns or revolutions per minute over the course of 10 seconds. Okay, so what I want us to do is let's find the angular acceleration and the number of turns that the wheel made during that 10 seconds. Okay, now, like I said, take the same approach that you would take if this was a regular kinematics problem. The first thing you do is you write down the things that you know. So let's read the problem and stop whenever we come to a piece of information and write it down in symbolic form. So a potter's wheel at rest. Well, so if it starts at rest, that means that its initial angular velocity, omega 0, is equal to 0. Okay, it spins up to a rotational speed of 100 turns per minute. Well, that's its final angular speed, so we will say that omega equals 100 turns per minute in 10 seconds. Obviously, that's the time. Okay. Find the angular acceleration. That would be alpha. And the number of turns in that 10 seconds. Well, the number of turns, that's angular displacement, so that would be theta. Okay, so now we look at the kinematic equations, and we see which one of them relates what we know to what we want to know. First, in order to find alpha, it appears that this equation, the second rotational kinematic equation, will do the trick. So we can plug numbers in. Okay. Omega equals omega 0 plus alpha t. Okay. Omega is 100 turns per minute. Okay, now at this point, when we start plugging in numbers, you have to be careful about the units. It's always important to use SI units so that you standard units, so that you end up with the correct units in your answer. In this case, the SI unit for angular displacement is radians. In fact, you might even want to put a note right here. Okay, the SI unit for angular displacement is radians, which means that the angular velocity should be measured in radians per second, because second is the SI unit of time. Well, this angular velocity is in turns per minute, not radians per second. So before we plug in the other numbers, let's convert this turns per minute into radians per second. Okay, now there's 1 minute in 60 seconds. So this minute will cancel that minute. Okay, and 1 turn around a circle is 2 pi radians. So 2 pi radians over 1 turn. That means that these terms cancel, and we're left with radians per second for omega. All right, get out the calculator here. We'll have 100 times 2 times pi divided by 60 gives us about 10.47 radians per second. Okay, so 10.47 radians per second. That's omega. That's equal to omega 0, which is given as 0, plus alpha, which we are looking for, times t, which is 10 seconds. So alpha is equal to 10.47 divided by 10, or 1.047 radians per second squared. That is the angular acceleration of the potter's wheel during the 10 seconds that it was speeding up. Okay, now we're also asked to find the number of turns that the potter's wheel made in that 10 seconds. Well, that is theta. So let's take a kinematic equation that will allow us to solve for theta. It looks like this kinematic equation will fit the bill. Okay, omega 0 is 0, so this first term right here is 0. Theta is going to be equal to 1/2 alpha. Well, alpha we just found is 1.047 radians per second squared times t squared. T is 10 seconds, so we square that. So I need to take the 1.047, and we will divide it by 2, and multiply by 10 squared, which is 100, and you get 52.3 radians. Okay, this is 52.3 radians. Okay, now I asked not for the number of radians, but I asked for the number of turns, so we'll need to convert these radians into turns. So let's multiply by 1 turn in 2 pi radians, so that my radians cancel, and I'm left with turns. So you take the 52.3, you divide that by 2 pi, and that gives us 8.3 turns. And that is an example of using the rotational kinematic equations to solve a problem. I emphasize again that if you get caught up in trying to have an intuitive understanding of just the rotational motion and looking at the Greek letters in the equations, then that might be intimidating or confusing to you. But if you remember, hey, this is just like using those translational kinematic equations. If I just treat this like a translational kinematic equation, then we'll be fine. Okay, one more piece of information for you, and that is that there is a relationship between the translational motion of an object and the rotational motion of an object. If you have a bicycle wheel that's rolling across the ground, then how far the bicycle goes is related to the distance that or the number of turns that the wheel makes. If you turn 1 time around, then the distance that you travel is 2 pi times the radius of the bicycle wheel. If you don't turn 1 time around, if you just turn some angle theta, then the distance your bicycle travels is equal to theta times r, where r is the radius of your bicycle wheel. Okay, so this is the general equation. If you've got a wheel that's rolling and it turns by some angle theta, then the distance that that wheel rolls across the ground is equal to theta times r, where r is the radius of the wheel. Okay, we can use similar expressions for velocity. V is equal to omega times r, and acceleration, A, is equal to alpha times r. So if you ever have a situation where you need to relate the translational motion of something that's rolling to its rotational motion, these are the equations that you use.